Well, hello, this is Mrs. Lemke here with video number 3 of our summer review. Getting to be halfway there, you guys. This is awesome. I love nerd jokes, so you do not get to be math team coach, one could say, without enjoying a little bit of math memery. I don't know if that's a word. But here are a couple for you to enjoy as we talk about derivative rules today. So today I'm just going to go through with you and see that you know the different basic rules for derivatives and then encourage you to do some practice, okay? So if you don't have a piece of paper and a pencil out, please have that and go get it right now if you don't have it. And then what I'd like you to do is to come back and try to write down the constant rule, the power rule, the product rule, and the quotient rule and the chain rule. Don't worry about the notation part. That's me just making sure that I remember to say something, but I'd like you to try to write those 5 rules. The constant rule, what's the derivative of a constant, the power rule, product rule, the quotient rule, and the chain rule. Okay, so pause the video, write those down as best you can using appropriate math notation, and then come back and we'll see how you did. All right, so let's see how you did with writing down the derivative rules from memory. The derivative of a constant is 0. The reason for that is if you think about this as a function, a constant function is a horizontal line, and derivatives mean slope. So if you have a horizontal line, its slope is 0. So that makes, hopefully, total sense. The power rule, you derive this initially through the limit definition of the derivative, but the shortcut rule that you learn is that the power ends up being down in front, and then the power is decreased by 1. This is true even if your exponent is a fraction or a negative value, you still decrease it by 1. If this were instead of an x, or something more complicated than an x, some interior function, like say you had sine of x quantity to the 5th power, then you would need to employ chain rule. But if it's just an x, this is what it is right here, as I've written it in green. Product rule, I always do it in the order of you have the first function times the derivative of the second function, and then you add to that so first derivative, second, so second, sorry, I had to say it to myself there, second function times derivative of the first. Now clearly, since addition is commutative, if you put this part, oops, sorry, I missed my pen. If you put this part first and then this part second, that's absolutely fine because these are being added together. I'm just telling you the order that I tend to do it in, just because that's the way, like, any answer key that I make will be written. The special case that I wanted to talk to you about is where you have a product, but one of the pieces of the product is a constant. So for example, what I mean by that in notation, I should say, is if you have a constant and then a function that is not a constant. Okay, so this is like 5 and this is like x squared plus 17 or something. If you were applying product rule to that, what would happen is you'd have first and then the derivative of the second plus second, and then the derivative of a constant, as we set up above in the purple writing, is 0. So since 0 times f of x is just going to be 0, we usually don't write this part. And this is sometimes listed in math books as its own rule, but it's really just a special case of the product rule in which the second part ends up zeroing out. All right, quotient rule. Okay, so one of the mistakes that I often will see with quotient rule is forgetting how to begin, because this derivative uses subtraction. So unlike product rule, it does actually matter what order you write things in. So you start with the bottom, derivative of top, minus top, derivative of bottom, and then the denominator is the old denominator squared. Again, this can be derived, but I'm just presenting it here as a rule that we expect that you know. All right, chain rule. Chain rule is what is used to take a derivative of a composition of functions. You can have as many layers as you want. All I'm writing here is the version of it being just 2 layers. So you take the derivative of the outer function, you keep the inner function as it is, and then you multiply by the derivative of the inner function. Oh, that's supposed to be a prime. If you have more layers, then you just repeat the process until you're through all of the layers. So I sometimes say it's sort of like sucking on a pretzel M&M, right? You first take care of the, like as you were sucking on a candy, you'd first taste that outer layer. So for a pretzel M&M, you taste the candy layer, then the chocolate layer, then the pretzel layer. And so it's like that. You take the derivatives in the order that they come, as if you were sucking on a piece of candy to take a derivative. The chain rule written in Leibniz notation, I think, is important to be able to write as well, in addition to this function with primes notation. Oops, ooh, I'm getting funky stuff. Okay, hold on. Okay, so here's one of those video lesson magic moments where writing just appeared. I was having a little technical difficulty. I think I pushed something I didn't mean to push. But I've written here now that we're trying to take the derivative of f of u, where f is a function of u, as you can see, otherwise we wouldn't say f of u. And then u is understood to be something more complex than just a naked x independent variable. It's u equals blah, blah, blah with x in it. Okay, so it's dependent upon x. The fact that our Leibniz notation out here, this symbol, which I actually didn't talk about back here, I've been using it, but I didn't talk about it. This d dx just means take a derivative with respect to x, meaning that x is your independent variable. So here it's saying take the derivative with respect to x, but over here I don't see an x. And so we have to know that u is denoted to be blah, blah, blah with x in it. It's dependent upon x. So the way that we would write this using just Leibniz notation instead of the prime notation would be to say we're taking the derivative of function f, treating u as the independent variable, but since we know that u itself is a function of x and we're trying to take the derivative with respect to x, we need to include the derivative of u with respect to x. So this is similar to what we did up here. We took the derivative of the outside function in terms of the inner function. The inner function is u. Here's my inner function. And then over here I have the derivative of that inner part, and this is the derivative of the inner part. So I like writing this out. First of all, AP definitely rewards you for knowing both of these symbolically, being able to write this out in both formats. But I enjoy pointing out that this part here is the reason that chain rule is called the chain rule. There is this link or this chain that connects the pieces. Right, on our next page, I have written out the 6 trig functions. I would like you to just see which derivatives of those you know. Hopefully all 6, but if not, just do the best you can. So I want you to pause the video again and then come back when you've written down the 6 derivatives as best you know them. Okay, let's peek and see how you did. All right, so a few things to note are all of the functions that have a prefix of cosine, and cotangent, and cosecant. Those all have negatives or opposite signs. And these come in pairs, although I did not especially exploit that in the order that these are listed. These two I say are related. These two I would say are related in pattern. And then these two I would say are related. They both have a square. Okay, and sort of a secant, cosecant, sound similar. So if these are things that you don't have in your head permanently memorized, please get them there and make sure that this time you keep going over them until you actually know them, the same way that you know the name of your dog or the lead singer in your favorite band or your mom's maiden name, whatever, okay? You should know it at that level, okay, so that you full on know it no matter what. You don't need to review it again. All right, again, these are some derivative rules that we would expect that you just have down pat. Rather than having you pause and write, for these I'm just going to write with you. So these are all the exponential and log derivative rules. And in this notation, the a means some constant. So a could be like 7 or 3 or something like that. And when you see e, that is the number e, that is the base of the natural log, 2.718, etc. And then natural log, as I mentioned, is the log base e. So we have, at first we have these two that are exponential functions, a generic base and then a specific base. And then the last 2 lines are a log with a generic base and then a log with a specific base of e. So if I were taking the derivative of a generic exponential, it has 3 components to it. It actually comes back containing itself, so a to whatever. And then it also would contain the derivative of the exponent. It also contains the natural log of the base. This next line is a specific or special case of that. It has all the same elements. It has e to the g of x, the derivative of the exponent, and then it would also have natural log of e, but natural log of e is 1, so we don't have to write that part. Okay, so usually we just say the derivative of e to a thing is e to the thing derivative of the thing. And that was this joke at the front here. So finding the derivative of e to the x is in fact e to the x, because x's derivative with respect to x is 1. All right, this next guy is a log with a generic base. And so again, it has 3 components. The 3 components are 1 over the function, the derivative of the function, and 1 over natural log of the base. And then if you have e as your base instead of a generic a, you would have all the same elements. And then because natural log of e would be 1, you don't need to write that last part here. Like this doesn't need to have anything else after it, okay? Sometimes we would write this just for consolidating sake, like this. Okay, so generally speaking, should know those rules. Okay, those are all the derivative rules I think we really need to review. These problems include some use of implicit differentiation. So I haven't mentioned that, but I did want to mention it as a warning. What I'd like you to do is to pause the video, and this is going to be a long pause because these are 5 longer problems, and then I'm just going to hit highlights, check your answers, and then we're done. So go ahead and pause the video and hold on the screen and just see what you can do with these 5. Okay, so the first one is a find the equation of the tangent line. And I hope that I can instill in you the fact that anytime you read those directions, you want to think, always, 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 I want you to think, I need a point and a slope. Anytime you read equation of tangent line is what we're trying to find, you think, I need a point and a slope. The way that we get slope is a derivative, and the way we get a point is the original function. So if you put 1 into this original function, you should get the point 1 comma 2. And then to get the derivative, to get the slope, you take the derivative, and so we would use our power rule for that, and you should get that the slope is 3. So f prime of 1 is 3, and then you use point slope form of a line, and then stop. Okay, a lot of times people have this like incessant need to simplify a whole bunch, and I understand that. I have those Scandinavian tendencies as well to want to straighten and tidy, and this is just not a time to do that. There are a lot of times that I read papers, and I'm sure Mr. Covey has had this experience as well, where students mess up the simplification. They had it right, and then they said too much. And you have to, as a teacher, then take off credit off of what would have been a right answer if the person had just stopped and not made a sign error or a distributing error or something like that. So please just stop when you've answered the question. Okay, question 2 was finding the derivative of that. And so notice that this is going to involve using quotient rule. We're going to start with this part on the numerator as our first little bit. And then when we need to take the derivative of the top, we're going to need to use product rule. So I don't have that all full, I guess I have it pretty fully written out. So this is what it should look like. And in the spirit of what I was just talking about, don't go there, okay? Just be done. This is a perfectly fine expression. If you are an engineer building a bridge, that expression will work just as well as that expression in any program that you're doing. All right, and then item number 3 says to differentiate that. It's important here that we rewrite a little bit because otherwise I think it's going to be really hard to tell what's going on. So this cube root we could rewrite. I'll do it a little bit at a time. The cube root we should rewrite as a 1/3 power there, and then the cube root on the inside we should rewrite as well. And we should have good parentheses so we can tell what's what. So this is certainly a chain rule problem. Our outermost layer, our candy coating of the M&M is the 1/3. Our second layer is going to be sine, and our third layer is going to be a power rule. And so the answer for that, kind of tidied up, is this. Okay, item number 4 involves finding a derivative with implicit differentiation. The way that we would know that is that this statement is not an explicit definition of a function the way that this was. F of x equals, f of x equals, f of x equals. Those are explicitly defining f of x. This guy doesn't say y equals or f of x equals. It has x's and y's blurred and mixed in together. So we need to just go at this with calculus rather than trying to isolate the y and then take the derivative. That would be difficult / impossible. So you go ahead and you take the derivative and understand that every time you see a y, you need to write a y prime as you're taking derivatives because of chain rule. You might have used the notation dy dx at those locations. That's fine. Some of you might have written a dx in a couple of places. Understand that that would be 1, and so you don't have to write dx over dx anywhere. Okay, so you take this derivative, and then they want to know, the question was to find the slope at, what was it? Slope at x equals 0. So if you put 0 in for x here in this original problem, you should be able to find out what y is. I think it's 1, is it? Is that right? No, -1, sorry. So if you put in 0, you should get that y equals -1. That is from the original equation. And then you can use that ordered pair, sub in, and solve for y prime. Okay, so the slope at 0, the y prime value at 0 is 1, and the ordered pair is 0, -1. So you put those two things together and write the equation of the tangent line, which is given there. Item number 5 was kind of messy. Okay, so this has e's and such. And this part here, I meant to mention this as, I gave you the question. I'm sorry, I forgot about that. Had a little bit of typing that's weird here, a little bit of lazy typing on my part maybe. This is what I meant for the equation to be. So if you didn't read it as such, pause the video and go back and make that adjustment. So this is x times y to the second. Okay, so when we take a derivative of e to a thing, the derivative is e to the thing derivative of the thing, but this derivative is going to require implicit differentiation like problem 4 did. Samesies on this bit over here. And then this, the derivative of sine, as we mentioned earlier in our lesson, is cosine. And so for that part, we are going to have cosine of y, we're going to have cosine of y and then a y prime or a dy dx. So the work for that looks like this. So this is e to the thing. This is the derivative of the thing, right? Using the rule for e to a function. This is keeping the e to a thing. This is the derivative of that exponent using product rule and a little chain rule. And then this is cosine of y times y prime. And then if you organize the pieces, okay, you have to do a little distributing and make sure all of the terms of the y prime are on the left side. And then every term that doesn't have a y prime, put it on the right side. And you should get this line, okay, factor out the y prime from all of the terms that have a y prime, and then isolate for the y prime. Now, that was exceedingly fast. I don't want to take too much time, but I also don't mean to plow over anyone. So of course you have had tons of experience learning from videos. Please go back, listen again. If you're confused at all, feel free to email Mr. Covey or me or both of us and just say, hey, I need some help on problem number 4 in video 3 or whatever it may be. And we're happy to help. But really what we're trying to do in this video is just make sure that you know all these derivative rules. These should be down pat, fully memorized, permanently memorized, not like you have to relearn them again. Okay, so make sure all 4 of those slides that I just flicked through, you've got that information down pat. And then the problems themselves were kind of tricky. If you found them not tricky, good for you. But if you did find them tricky, go back through them and make sure that you're confident. We want the year to go very well for you and get you off on the right foot. If you would like more help, definitely go back to your math analysis review packet. I know that I helped some people in the spring in the MRC, saw an excellent review packet that you had. And if you still have that or can find it online, that would be awesome. And just take a look. Or if you can't find that and do want more practice and can't seem to find any, again, just email Mr. Covey or me and we can find some for you. Okay? Thank you so much.